Hello, everyone. My name is Hans-Jürgen Schönig. I'm the CEO of Cybertech, and hopefully for this year's conference, I've prepared some really interesting performance stuff you've never seen before. So if you're seriously interested in performance, check out this talk and learn something that is way beyond just adjusting some Postgres configuration parameters. Have fun. So hello, everyone, and welcome to this year's conference. My name is Hans-Jürgen Schönig. I've been in professional Postgres for 25 years. And I guess this is a follow-up talk to the presentation I gave last year, which was about performance features you've never seen before. Just to prepare you for stuff, I hope you've never seen many of those things before, because the intention is really that you learn something new, that there is something interesting for you, and that there is certainly some content that goes way beyond just changing some memory configuration or something stupid like that. So let's hope it's interesting, and let's get started. As far as my background is concerned, we at Cybertech here, we're running a worldwide Postgres consultancy company. We do support, training, all kinds of Postgres development, etc. And we're based here in Austria, but we're operating internationally. But let's get going. Postgres performance. Let's share some things which are new. And as I've mentioned already, the goal of this talk is really to give you some trickery that some old Postgres consultant would use, or to give you some things that might be thought-provoking, or to show you some stuff that is just more than there is bad performance, throw in memory and CPUs or add disks. I mean, of course, disks and memory are never a bad idea, but there's a lot more to that. So as a Postgres consultant for 25 years, I can assure you there are things that are way more interesting than just throwing memory at the problem. So let's do a little tour through Postgres, and I will show you some random stuff that can be super beneficial and that might be a little bit eye-opening and hopefully entertaining and interesting. So let's get started. Just like last year, eventually everything starts by creating a simple connection. So people might wonder, okay, what's the point? We're creating a connection. We're doing basic stuff. How can we speed it up? But let's take a look at a variable most people might not have seen before. It's called session preload libraries. And what's this thing? How does it work? So let's get started. So imagine, as you know, in Postgres, you can write stored procedures in many different languages. You might write stuff in PostgreSQL, you might write it in SQL, you might write it in Perl, Python, whatever. But if you're doing some kind of machine learning or statistics, or if you just happen to like R code, there is an extension out there. It's called PLR, which allows you to write stored procedures in R, which is perfect for all kinds of statistics and machine learning and all kinds of fancy math. So if you are doing finance, or if you're doing biology or anything of this kind, R is perfect for you. So what's the problem here? So I've written a very simple function. It just says if this value is greater than the other one, return this one, otherwise return the second one. Well, what's the problem here? Let's take a look. When I'm running this function after creating a connection for the first time, you will see that this simple function will take 229 milliseconds on my machine. If I call it for a second time, and you can see it's absolutely the same thing, it has gone down to way below a millisecond. And this already includes parsing, transfer time, permissions, everything there is. So obviously we are a couple hundred times faster on the second call. And imagine you're creating hundreds of connections, and every time you create a connection, and when you do the first call, Postgres has to load this library and initialize it. And this is exactly when we can go for shared preload libraries. What it does is, instead of loading the library during the first call, what we do here is we load the library already when we create the connection. So what we do here is basically we move the expensive part from user experience to the background, right? So it's still not free on first call, but it's already a lot better. And the real life example for that would be PostGIS. So if you're running some kind of application that is using geometric data, PostGIS is the industry standard in the open source world to do GIS data. And if you're doing a calculation based on geometric data, this setting can help you a lot to improve user experience, because there will be many, many first calls when you call your first PostGIS function. So the first thing is shared shared preload libraries to improve on the first call to your connection. But let's see what else there is. So what you can see here, 10 milliseconds, 0.6 milliseconds. If we use the library, what you can see is that the first call is more than 3 times faster than originally. So obviously there is a benefit to that when we engage with this variable. So let's move on to the next one. It's about storing data. So it's not only that we can improve the situation when we create the connection, we can also improve stuff when we run stuff and when we store data. In Postgres, there is a tool called pgbench, and we can use that to basically run a synthetic benchmark and see what it does. So in this example, I've initialized a small test database, and I'm running 4 concurrent connections, 25,000 transactions, and our pgbench thing will get 4 threads. So we're running basically 100,000 transactions. And what we see here is 2 variables. The first one is the wall level, which is related to the Postgres transaction log. And the second one is also max wall size, which is also related to the Postgres transaction log. And what we'll compare is logical versus minimal. And then we will run the same thing with 2 different settings for max wall size. So let's see what happens. If we run this stuff with full transaction log, for logical decoding, for streaming replication, for binary backups, etc. And if we run that at the minimal wall size, the very small wall size, our 100,000 transactions will produce 130 megabytes of transaction log. What is pretty cool here is that this PG current wall LSN will give you the position inside the transaction log. And what is really, really nice in Postgres is you can use these data types and run calculations. Right? So obviously what we did is we take the current transaction log position, subtract the initial 0, right? And then we see that it's 135 megabytes, which have been created since the start. But let's imagine we only have a single server, no streaming replication, no logical decoding, no backup, just a simple local test machine, which you might use for some embedded operations, uncritical data, whatever. We could change those settings and see what happens. 135 megabytes all the way down to 82 megabytes. So by just reducing the wall level and by increasing max wall size, we can actually not just improve performance, we can also shrink the amount of transaction log that is written to disk, which will in turn make things smaller on disk, make things faster, reduce all kinds of overhead there is. And the question is, why did it happen? And there are actually 2 reasons for that. First thing is, minimal puts less stuff into the transaction log. And max wall size, by making it larger, what it does is it will increase checkpoint distance. And that actually means that we don't have to write so much transaction log, because the rule is, if an 8 kilobyte block in Postgres is touched for the first time after a checkpoint, we have to log the entire 8 kilobyte block and put it into the transaction log. Every additional subsequent change, what has to happen is we only log the difference, right? So if you touch a block more often, you will basically increase the chances that the first time after a checkpoint happens. So it's fewer full page writes, and that will actually decrease the size of the transaction log. So by increasing max wall size, actually we also already optimized the your write operations, because there's not going to be so much volume that's going out there. So increasing max wall size means we're often able to reduce the size of the transaction log, but we're also often able to just do all kinds of other trickery that makes life a lot better here. So this is excellent. So you might try it out. Big max wall size entries. You will need more disk space, but it can make your database application so much more efficient by reducing IOPS, right? Next thing is indexing. What people often forget is that indexing is really the most important thing on this planet when it comes to database performance. Without indexing, there is no such thing as database performance. It just doesn't exist, right? It doesn't exist, no matter what. Hardware is not going to fix the problem. If indexing is broken, you're doomed to suffer, right? There is no other way. And let me elaborate on that using a simple example. So imagine you have 1,000 queries that take 1 millisecond, right? So 1,000 good queries, 1 millisecond each. This is going to take 1 second. But if there's one traitor, one bad query that takes 1 second, right? This means that it's 50-50. 1,000 queries produce 50% of the load, and one nasty query will also produce 50% of the load. Okay? So one query can be super responsible for this entire database performance thing, right? So indexing is important, because what we really want to do is get rid of this expensive query, because it will double our speed or half our load. So super important. So imagine those 1 millisecond queries would all of a sudden take 1 second. I mean, you had to put in 1,000 CPU cores to make this happen. So it's not like you add 1 CPU core and everything is golden. It's really, really important here. So what can we do here? Let's generate a table. It's called tstatic. And let's import 25 million integer values. Very simple, 25 million integer values. Everything is golden. So when we create an index here, what happens is that by default, Postgres is going to build this index in a way that those entries in our index pages are only filled up to 90%, right? And the reason why we do that in Postgres is that if you create an index and then you insert a value, what we want to do is you want to avoid that those pages have to be broken apart because there is no place anymore. So we want to avoid page splits immediately after index creation. So by default, Postgres will make the index, but it's only 90% full. So often data is absolutely read-only. So imagine you have a phone book, you got history books, you got anything that is certainly never going to change. No imports, no inserts, just historic data. You never touch it. It's just there, right? You don't insert, you don't update. You just have static data set. You index that, you never touch it again. What you can do in this case is you can use a fill factor and say, hey, Postgres, make sure that your index is super, super full, not just 90%, but make 100%, because we know that there are not going to be inserts and updates all over again. And this will basically reduce the size of your index by, say, 10%, because you're filling up all the pages. And this can give you an additional performance boost because you're making things slightly smaller. And this is wonderful for static data. Don't do it on data that is constantly modified. because that's the reason why the default value is 90%. But if something is really, really static and historic, you can increase the fill factor to make it more efficient. So again, this is the summary, 90% because we want to avoid node splits, and 100% if something is super, super static. So this also a couple of percentage points, you can get it for free, and everybody is happy. Next thing is, so we've created a connection, we've loaded some data, we index the thing. So next thing we want to do is maybe we want to run a join, right? We want to run SQL statements, we want to run joins, and we do so possibly millions of times. So this is really fancy. I like this a lot. I learned that from a guy in the Czech Republic. Excellent stuff. Let's imagine you run an SQL statement that generates SQL statements, right? So we do select, create table. So we basically generate the SQL. You can see from line number 5 to number 9. And what PSQL, the command line client for Postgres, can do is it can do \gexec. What it does is it uses the last result set you got and assumes it's SQL and executes that. So we create 5 tables. We generate the SQL statements for those create table statements. We run \gexec. PSQL is going to throw this back to the server, create five tables, and off you go. So you can basically generate your SQL statements, execute them directly without even leaving the command line. So we've created 5 tables in a very nice way. So, word of caution. What I'm going to show you here is slightly dangerous. So you should really know what you're doing here and understand this type of stuff, because otherwise it can really backfire. Okay, just a word of caution. Everything planner related can be good or bad. Depends on how you do that. So let's take a look. Let's have a query that says select star from X1, X2, X3, X4. So we're joining 5 tables. And what we see here is that the execution time is 0049 milliseconds, but the planning time is 6 times higher. So obviously, if we have a query that doesn't involve a lot of data, but does a lot of joining on empty or basically empty tables, planning time, just for the optimizer to decide on the strategy, is going to be super, super dominant, right? So planning time can be a lot longer than execution time. So the question is, can we do something actually to tell the optimizer, hey, don't dare to be smart here. Let's be stupid. And this is a thing which is rarely understood. It's called join collapse limit. Most people have never seen this stuff before. And what it does is, what we see here is X1 join X2 is an explicit join. So basically it says join X1 with X2 and then with X3 and so on. But Postgres says, you know what? If you write an explicit join, I'm still going to optimize that for you. And what we see here is X1 is X2, X2 is X3, X3 is X4, X4 is X5. So Postgres figures, hey, X1 is really X5, and X4 is X2, and X3 is X4, and etc. So it will implicitly compute something we call equality constraints, and try out all the join orders to figure out which one is the best one. By setting join collapse limit, what we do is we tell Postgres that don't change the join order for explicit joins on your own. Use the join order I've given you. So this can be super dangerous because you might end up with a suboptimal join order. But if you know that this is the way this join has to be executed, you can set join collapse limit and nail the execution plan the way you want that, save on planning time, improve performance, 5-fold, 2-fold, 50%, whatever. And have an efficient plan that is basically running locally. Yes, there is such a thing called prepared statements, But this is really for queries that are really fully planned or first-time planning, stuff like that. Okay? Next thing is we've created connections, we've loaded data, we've indexed, we've run an SQL statement, we've planned the SQL statement, and now it's time to execute the SQL statement. So let's see if we can maybe do something here that will change this stuff for good. It's a bit hard to read, but let me put it on one slide. I'll create a table, empty, 10 million entries, right? So t-test, generate series, 10 million entries. So we got 10 million numbers. And what you see here is basically two identical functions. One is a return many function, and the other one is returns few function. So it's the same function. The only difference is in line number 11. In the left function, it says, if the number is even, return the value. So it returns 50% of data. So you feed it a million rows, and in 50% of all cases, it will say, okay, let's do that. The other one does modulo 1,000 equals 35. So it's not going to return 500,000 rows if you throw a million at this stuff. It's only going to return 0.1%. So obviously, both functions do the same, but the odds of returning stuff are way higher on the left side. So if you run a query that says, select everything from t-test where returns many equals ID, and then returns few equals ID, what it means is that Postgres doesn't know that those functions are different. So it will just execute them in the order we put them. So it will call the returns many function 10 million times. It will return 5 million rows. So we will feed 5 million rows to the second function. That's bad, because if we executed the returns few function first, there wouldn't be anything left for the returns many function, right? So obviously, by changing the execution order, by doing the few function first, the overall effort goes down, because the function that returns more data is simply not called often anymore, because there's nothing left. So let's see how we do that. So what you see is obviously we call this one 1 million times, we call the other one 10 million times, we call the other one 5 million times, and you see that overall it's 2.3 seconds of execution time, or 2.4 seconds. So let's try something. Let's do alter function, return many, cost 1,000. By default, Postgres assumes that function call is 100 times more expensive than an operator. So if you do A equals 10, it has a certain cost. But if you do function equals 10, Postgres assumes that this is 100 times more expensive than an operator. But now we're telling this thing, you know what? This is not 100 times more expensive than an operator. This is 10,000 times more expensive. So obviously, the price for return many from the optimizer point of view has just gone up, while the cost of the other function has gone down. And what Postgres does is, instead of running this for 2.6 seconds, it only needs 2.1 seconds now, because obviously the returns few function is called before the returns many function. So we changed execution order, but just assigning different cost to those functions, right? And this will obviously give us the chance to influence performance in case we got many stored procedures. So this is how it works. There's a thing called CPU operator cost, and it's multiplied. And what we do is basically we influence the behavior of those functions. What we do is we just change the relative costs of things to each other, okay? So this is not absolute cost. This is about relative cost. Okay, so that was my features, which you hopefully have never seen before. creating connections, loading data, running, planning SQL, indexing, planning SQL statements, executing them, and finally, some magic for stored procedures. I hope you've enjoyed that, and hopefully we will see each other again. But before we see again, we are actually hiring. So we're looking for Postgres engineers, support people, consultants, migration specialists, whatever you like. So feel free to send me a message, and I hope you had a nice conference. I hope we will see many other interesting presentations. And thank you for your attention, and looking forward to getting in touch with you. So just send me an email, share this talk with your friends, and recommend this conference to everybody you know, because it's really a sensational event. And hopefully see you next year.